Hello there. In this video, we are trying to demonstrate buffer overflow attack on a 32-bit 14.04 Ubuntu system based on x86 architecture. This will be done with the help of GDB. Buffer overflow is a security threat wherein writing to a buffer might override the adjacent memory location. We will first explain the given assembly code that implements a shellcode. This shellcode uses relative addressing. The shellcode calls execve system call. Execve runs an executable file in the context of an already existing process. From the man page, we can see that execve takes three arguments. The first is a pointer to the file name. Second is an array of char pointers, first of which should be the file name. And the third is the environment variables, which is an array of char. An important thing to be noted is that both argv and envp must be terminated by a null pointer. Now let us look at the code. When jump line statement is executed, we jump down and execute call address statement. When a call instruction is executed, the instruction following it is pushed to the stack as the return address. Thus, the top of the stack is a pointer to the ASCII string /bin/sh. After this, control of execution is transferred to the first instruction under the address label. This is where the call to execve is done. Execve has system call number 11. Before calling the interrupt, we store the first three arguments in EBX, ECX, and EDX respectively. Thus, EBX would be a pointer to the file name, ECX would be the array argv, and EDX would be the array envp. The PowerPL instruction stores the top of the stack into ESI register. Thus, ESI now points to the string /bin/sh. At an offset of 8 from ESI, contents of ESI that has the address where string /bin/sh is stored. The next instruction indirectly stores 0, that is null, into EAX register. This method is followed to avoid null characters from appearing in between the shellcode. This null is stored at 12th offset from ESI. It is also used to null terminate the /bin/sh string at offset 7. The hex constant, hex b, is stored into AL so that EAX contains the system call number. The ESI value is stored into EBX, the 8th offset from ESI is stored into ECX, and 12th offset is stored into EDX. After which, control is given to interrupt vector hex 80, which then executes the execve system call. On return, the exit system call is made so that the program exits gracefully. The next task is to translate the assembly code into machine instruction bytes. This is done by wrapping assembly code instructions in a GCC ASM instruction and displaying the compiled code using objdump-d. Let's compile the code using GCC. Now the machine code is displayed using objdump-d. You can see the machine code and it is now copied and then we format it. Now let's execute the machine code using the given C program. The formatted machine code is stored into the character array shellcode. Now let's run this program using GDB. First, before executing, let's compile it using the following flags which are set. FNO stack protector flag to disable Stack Overflow security checks. Exec stack flag makes all the pages executable, not just the stack, and the position independent executable flag to allow ASLR. ASLR is a defense mechanism implemented by recent Linux kernels that randomize the start of the segments that include the stack segment. Once it is compiled, the program is executed using GDB and the bash shell opens up as expected. Next, we will launch our attack on the given vulnerable code. The vulnerability arises because there is a possibility that string that is copied into the buffer might exceed the buffer size and end up overwriting the stack contents. If used cleverly, the return address can be manipulated to execute malicious code. You can think of this program as receiving the shellcode somehow and calling the vulnerable function foo within. Before executing this program, let's ensure that ASLR is enabled in the GDB environment. Now let's run the executable using GDB. While compiling the program, the flags are once again set just as we have done previously. Without overwriting the return value on the stack, we can see that the process exits normally. Now let's proceed with the buffer overflow attack. First, we insert a breakpoint at foo function. Now, let's see what is the starting address of the shellcode. The return value is stored at offset 4 from EBP. It is overridden with the starting address of the shellcode using the following command. We continue the execution and now the bash shell opens up successfully. We'll repeat the above process a second time to show that ASLR works and the address of the buffer changes with each execution. You can see that the address has been changed. Let's set the EBP value and continue the execution. You can see the bash shell has been opened. Thus, we have successfully done a buffer overflow attack on a vulnerable program. Thank you.